All right, today we're diving into something called MolmoAct. It's a new model that's trying to teach robots to do something that sounds simple, but is incredibly hard, to actually think before they act. We're talking about giving them a kind of spatial reasoning.
So here's a question that's probably crossed your mind. Why is it that an AI can write a whole novel, something incredibly creative and complex, but we still don't have robots that can just reliably load a dishwasher? It's a really weird paradox, right? Language AI is just soaring. It's flexible, it's general. But when it comes to the physical world, robot AI often feels stuck. It's brittle, it's super specific, and it fails at what look like basic chores. What's going on here? So here's how we're going to break this down. First, we'll look at why robots get tripped up so often. Then we'll talk about how we plan our own actions. After that, we'll get into the good stuff. A robot that actually thinks. We'll see how it does in some tests, look at a really cool feature where you can steer its plan, and wrap up with what this all means for the future. So let's jump in.
Okay, Section 1. Why do robots still stumble? You might think the main problem is just not having enough data, but it turns out the real issue is something a little deeper. It's about a lack of structure.
See, a lot of robot AIs right now work kind of like this. They see an image, you give them a command, like pick up the cup, and they try to spit out the right arm movements. It's a direct line from seeing to doing. But the problem is, it's often a total black box. We have no idea why it decided to move its arm in that specific way. And because we can't see its reasoning, the whole system is fragile. It breaks easily, and it has a really hard time adapting if anything changes.
All right, so to figure out a better way, let's just think about how we do things. Take something simple, like reaching for your coffee cup right now. It feels automatic, right? But underneath, your brain is running this incredibly elegant little program.
It happens in a flash, but there are basically 3 steps. First, your brain just gets the scene in 3D. You don't see a flat picture, you see a world with depth. You know exactly where that cup is in space. Second, you mentally sketch out a path for your hand. You don't even think about it, but you're planning a trajectory. And finally, you turn that mental plan into a smooth physical motion. See? It's this beautiful, seamless flow, from seeing to planning to actually doing.
And that is the key. That 3-step process is exactly what MolmoAct is trying to copy. It builds a structured pipeline that, for the first time, really lets the robot think before it moves.
And check this out. This is the real aha moment. Look how perfectly this mirrors what we just talked about. Step 1, depth perception. The robot figures out the 3D layout from its 2D cameras. Step 2, it creates something called a visual trace. This is basically its plan, a little sketch of where it's going to move. And step 3, it takes that plan and turns it into the actual motor commands. It's the same logic.
So let's dig into that first part a bit. How does it see in 3D? Well, it uses a specialized AI that looks at a normal 2D camera image and basically summarizes the 3D information. It condenses it down into this compact code, a series of tokens. You can just think of them as a special language the robot uses to understand space.
Now this visual reasoning trace, this is the magic part. It's literally the robot's thought bubble made visible. It draws a line on the screen showing where it plans to move its gripper. And this is so important. It's not just a cool visual. It forces the robot to actually create a spatial plan, and critically, it lets us see what it's thinking before it even moves. So when the robot finally decides what to do, these final action commands aren't just a knee-jerk reaction to what it sees. No way. They are guided and informed by both its 3D understanding of the scene and that visible plan it just created. It's a much smarter, more deliberate process.
Okay, that all sounds great in theory, right? A robot that thinks. But does it actually work any better? Let's see what happened when they put it to the test.
So in the real world, when they pitted it against another top model, the results were pretty clear. MolmoAct got a solid 10% boost on single-arm tasks. But look at this. For tasks that needed 2 arms, bimanual tasks, it was almost 23% better. That's a huge leap, and it shows that this planning ability is a real game changer for complex coordination.
And it's not just about single moves. When they tested it on tasks that require a whole sequence of steps, long horizon problems, it still came out on top, beating the next best competitor by more than 6%. This really proves that its ability to plan ahead pays off when the going gets tough. But for me, this is the most impressive part. What happens when you throw it a curveball? Change the wording of the command, add distracting objects to the scene, or even give it an object it's never seen before. Well, it handles it way, way better. Look at those numbers, a 30% improvement with novel objects. This structured thinking makes it so much more robust and less fragile than the old black box models. Okay, so because the robot has this visible plan, this thought process, it unlocks something truly groundbreaking. We can actually reach in and steer its plan. Think about it. Language is messy. If you tell a robot, pick up the bowl, but there are 2 bowls on the table, what's it supposed to do? This kind of ambiguity is a classic problem that trips up robots all the time.
But with MolmoAct, we get to see what it's thinking. The robot generates that yellow line, its visual trace, and you can see it right there on the screen. Oh no, it's heading for the wrong bowl. But the key is, this is all happening before it moves. We can see its mistake before it makes it.
And fixing it is brilliantly simple. You don't have to try and rephrase your command like, no, not that bowl, the other one. You just take your finger or a mouse and draw a new line, this cyan trace, pointing to the right bowl. You are literally redrawing its thought process. It's that direct.
And guess what? It works. This visual steering method has a 75% success rate for fixing these kinds of ambiguous situations. The researchers found it was way more reliable than just trying to use more words. It's a completely different, much more intuitive way for us to work with a robot.
So what does this leave us? What's the big picture for robotics? Well, maybe the most important part of this whole story is that the team behind it is making it completely open.
And when I say open, I mean everything. The model itself, the code used to train it, even a brand new data set with over 10,000 robot movements, it's all out there for anyone to use. This isn't just one team showing off a cool new toy. They're handing the community a blueprint for building robots that can actually reason.
And it really all comes back to this quote from psychologist Barbara Tversky: "Thinking is embodied, spatial, and outside your head." That's the whole philosophy here. For a robot to interact with the world, its thinking can't just be some abstract thing happening on a chip. It has to be grounded in the physical, spatial reality of the world around it.
By making a robot's thought process something we can actually see and even guide, MolmoAct is kicking open the door to a whole new way for humans and robots to work together. Which leaves us with a really exciting question to think about. If we can see what a robot is thinking, and we can help steer it, what could we build together? What does that future look like?